So welcome back. So we just finished off this guy, and this is one of those questions where I know I'm going to ask you this question on the test. So just learn it and learn how to do it, and it's money in the bank. So you know it's coming. Just make sure that you're prepared for it, and just learn the skill, and it will pay dividends. I'm trying to really encourage you to build up your skill on this so that it sets a stronger foundation. Notice I could have just given you the displacement vector. I could have given you R3, and then you wouldn't have had to go through these other steps. You know, there's three levels. I give you R3, and R3 is in the same direction as the force you're interested in. Or I could give you R3, and R3 is in the opposite direction to the force you're interested in. Or I can give you the displacement vectors for the two charges from the origin, and then you have to go through this more convoluted way to discover R3, and there's no, any one of the three is possible. So don't learn the difficult one and then not be able to do the easier ones. You know how to get ready. A point charge X is located some distance from a point charge Y. So let's visualize this a little bit. So here's my X, and here's my Y. And it says the charge X experiences a force of 18 newtons towards Y. So this is that, and that is 18 newtons. I'm asking you some conceptual questions here. So what can you conclude about the sign of the two charges? Anybody? They've got to be different, haven't they? Yeah, because if they were the same, either two positives or two negatives, then they would be a repulsive force. So they must be different. That's at least what you can say. And then what size of force is experienced by charge Y? So what would we have? Anybody? It's got to be 18, because good old Newton's law says equal and opposite. So that would be 18 newtons. So what direction, well, I just did it, didn't I? What direction will the force on charge Y point? And it's going to be towards charge X, because they're attractive forces, so we know that. Agreed? And then what can you conclude about the magnitude of the two charges? So I should have given out the clickers and I didn't. So the two obvious choices are they're equal. And the other is that the other extreme, which is you can't tell anything.
Is it worded like the magnitude of one is equal to the magnitude of each, or both together?
Well, I mean, it says X equals Y, or
no, just the question itself, like of the magnitude of the two charges together, or the magnitude of each of the two charges.
But look at the answers. I'm asking you to compare them. Okay. Yeah. So yeah. Yeah.
The magnitude of the forces between the charges, or the actual charges?
What the charges, not the forces, the charges. We know that the two forces are the same size, don't we? We know they've got the forces of the same magnitude. So the question is, if you have forces of the same magnitude, do you have charges at the same magnitude? And so I have to ask you, is the pull on the Earth the same as the pull of the Earth on the is the pull of the moon on the Earth the same as the pull of the Earth on the moon? Have they got the same amount of mass? No. And the fact is, it does not matter. The force of your truck on the love bug is the same as the force of the love bug on the truck. You don't have the same masses. You cannot say anything about the charges if it's electrostatic. You can't say anything about the masses if it's gravitational. So you can say nothing. And that's the conceptual kind of. Okay. Excuse me. Okay. Point charge is located at some distance from point Y. So there's X. Please. It's right on the edge of my hearing, and it's like I'm catching it now. So please. Charge X experiences a charge of 18 newtons towards charge Y. So this is 18 newtons. What force would charge X experience if the separation between two charges were tripled? And the way you do this is you say, well, what's the expression? Fe is equal to Ke Q over R squared. Here I'm using big Q for one charge, little q for the other charge, over R squared. And I am tripling the separation. So some people can look at this and they can say, if I'm tripling R, that means it's going to be 1 over 9. So they say it's going to be 1/9 of 18, which will be 2. Some people can do it in their heads. For other people, they can't. So we can say that Fe new is equal to Fe old over 9, which equals 2 newtons. Some people can't do that, and so they've got to use this next technique. And I'll show you this next technique in a more complicated version. What force would point charge experience if the separation between two charges were tripled, the magnitude of charge X were doubled, and the magnitude of charge Y was quadrupled? And not many people can do that in their heads. But what we do is we do it like this. We say, remembering that, we say F new over F old, it's asking me for a new value, is equal to F new over, it used to be 18, and then this is going to equal Ke new over Ke old. That's not going to change, but even so, times big Q new over big Q old, little q new over little q old, separation new squared over separation old squared. So I'll put the new over the old. And then it's kind of like some people like to, they call everything that doesn't change 1, because it doesn't matter. And other people like to write it down and change it. So I'll go Ke new, Ke old. I'm going to cross those out because they cancel each other. But you could put down 1 and 1. One of the charges, the magnitude of charge X is doubled. So let's call that one 2 and that one 1. It could call it 200 and 100 or 2,000 and 1,000 or 56 and a half of 56. It doesn't matter as long as the ratio is 2 to 1. And then that one is quadrupled. So that would be 4 and that would be 1. Again, you could do 20 and 5 or 4 and 1 or whatever you like. And then this is tripled. So that's going to be 3 squared, and that's going to be 1 squared. So this works out to be 2 4s are 8 over 3 3s are 9. Now, I can't tell you how many people then tell me the answer is 8 over 9 newtons, but it's not.
Time 18, right?
That's right. Fn over 18 is equal to 8 over 9. So Fn is equal to 8 times 18 over 9, which equals 16 newtons. So don't, and that's layout. That mistake is layout. It's if you're doing things in your head and you're not laying things out, it's very easy to forget that way back when you knew the answer was, the old answer was 18. It's way back when. And so that's why I'm encouraging you to practice layout. That's why those skills homeworks, they're pretty easy, but they're basically drilling you in laying things out and laying things out and laying things out. It's really important. Cool. Let's make it a bit more interesting. So how can we make it more interesting? Let's add a whole bunch of charges here. So we have a charge of interest, which I guess is Q, and we have, you know, a big Q2, a big Q3, a big Q4, and they're kind of like, I'm thinking of those as been like stable and stationary, and then this little q is the thing I'm interested in. The net force on charge little q experiences due to a group of point charges equals the sum of the electric forces, the vector sum caused by the individuals. So I've got to imagine a whole bunch of arrows on here. Let's say I already have the arrows. So I say, well, it's going to be, here's in math language, it's the vector force is equal to the sum of all the individual vector forces, which equals the sum, and for each vector force it's ke little q times big Q over r squared times the unit vector in that direction. So I'm going to sum all these vector forces together and I'm going to express it like that. It looks involved. And this is something where I want to show you this because it tends to be what the textbooks tend to like. And I have some issues with it because it's a bit, it teaches you about symmetries as much as anything else, but it's not generic enough. It's not generic enough, but this is what they tend to like. They'll say, we have 4 equal positive charges, and they'll lay at the points indicated in the diagram, and if you look, it's a 2 by 2 by 2 triangle, so it's an equilateral triangle. Is that right? Or isosceles? Equilateral, good. And the magnitude of the force experienced by charge X, there's charge X, because of charge Y, there's charge Y, is equal to 3 newtons. Okay. What is the magnitude and direction of the forces experienced by charge Z? Oh, I see. Here's the trick. You can take any 2 pair of charges in isolation and just think about them. So there's going to be a force. It's going to be repulsive because they're all positive. There's going to be a force on Z caused by X. It's going to be along the line joining X and Z. There'll be a force on Z caused by Y. And there'll be a force on Z caused by W. And I know, because of that language there, what the size of this force is. It says the magnitude of the force experienced by charge X because of Y, X because of Y is 2 meters away. If you're 2 meters away, that's the force you get. Well, look, we're 2 meters away, we're 2 meters away, we're 2 meters away. Oh, I see. 3 newtons, 3 newtons, 3 newtons. Then it says, what is the magnitude and direction of the force experienced by charge Z? So I've got to sum these vectorially. And so the way you do that is you use components. I could use IJK, but it'd be a bit more involved. So let's go and do not an eraser, sorry. Let's go there. So what we do is we find our way back and we say, well, let's have a look. That's going to break down into that component. And that's going to be, if you like, Fy. That would be minus Fy. That would be Fx. Fx. These 2 Fy's cancel. So it's these 3 I'm interested in. I say, well, the total F total is equal to, let's have a look at this. It's going to be 3 plus, that's that one taken care of. This is a 60-degree triangle. So that's 60. That would be 3 cosine 60. And that's 60. So that would be plus 3 cosine 60. So F total is equal to 3 times plus 1.5 plus 1.5 is 6 newtons. And these are all pointing to the right. And I think it's a bit of a con because there's too much symmetry in there, but that's the game they're playing. Very often you see it in the back of the chapters. They like that kind of question. I remember seeing it when I was an undergraduate, and you know, it's still in the books. Okay. But in principle, you could take, you know, I could give you a positive 6 and a positive 3, and I could put down a positive 1, and you'd say there's one force and there's another, and you can work out the ijk for that. You can work out the ijk from that and just add them together. Agreed? So forces, we can work them out as magnitudes, we can work them out as vectors. We add them vectorially. They work. So let's talk about electric fields. And if you're anything like I used to be, I would say, oh, why bother? I can do forces, you know, I'm happy. And it turns out that electric fields are really, really, really useful. Nothing in your textbook is there just to fill space up. So if it's introduced, it's there because it's got an advantage for us. And the problem is it's a little bit abstract. When I talked about that sphere of influence and how it diminished as it got further away, because the same amount of stuff spread out over a larger and larger sphere, I was talking about the electric field. So you can say, oh, the electric field is this influence, the electrostatic influence, and that's kind of honest in a way. At some point you've got to quantify the electric field. How much, how strong is this electric field? And so we turn around and say, well, the electric field is the amount of force per unit charge that a charge would feel there. So the units for electric field, E has units of newtons per coulomb. So it's tempting to define the electric field by that picture. You have a mother charge and around it is space, and you point to a point in space and you say, well, a 3 coulomb charge here would feel 6 newtons. So that's a 2 Newton per coulomb electric field. And it's confusing in a way from the start because, but there's no charge there. You know, it's like there's not a charge there. Where did this charge come from? This second charge, what's going on here? And it's there to give you a magnitude. It's there to kind of help with visualization. But if you're not careful, it's a confusing help. So think of the electric field as being the amount of influence, the amount of electrostatic influence. And recognize it is abstract. And we can get a handle on it by saying it's the force that a 1 coulomb positive charge would feel, but it is the influence. It's a bit like talking about the it's a bit like talking about the gravitational field, little g. That's exactly the same thing. Pick a point in space near the Earth's surface and you say, what would the force be on a 1 kilogram mass here? And you go 10 newtons, because little g is 10 newtons per kilogram. Problem with that is we get so used to it being always 10 newtons per kilogram, we forget that if we go further out, it gets less and less and less. We don't do enough of those problems where we go into values of little g other than 10. Fair enough. But recognize the fact that gravity is not there because the little 1 kilogram mass is there. Gravity is there because the Earth is there. And so the electric field is there because of this big Q. And I can interrogate it by imagining a little q being here, but there don't have to be a little q there. It's to do with that point in space. We said electric field can be considered as an aura that surrounds the charge and is a storehouse of energy. The electric field strength, big E, which is the equivalent to little g, you know, mgh, that little g, that was a gravitational field vector actually. The electric field strength E at a point in space is numerically equal to the electric force that would be experienced by a unit positive charge at that location. We have to pick now Before we could just say 1 kilogram. 1 kilogram positive, 1 kilogram negative. No, kilograms are always positive. Now we have charges, and we can have positive charges and negative charges, a bit like matter and antimatter. You know, it's like, whoa. So then, okay, it's a bit more complicated. The electric field, so here's my drawing of it. So here's my mother charge. I'm picking this point in space, and I am imagining putting this little test charge there and saying, what force would it feel? Well, it's going to be a repulsive force. I draw a little vector in the same direction as repulsive force, and I call that my electric field vector. You want to know the size of it? Electric field vector is equal to the force vector divided by the little charge. That should be Q naught. It's that charge. Whatever I imagine putting in there. It's nice if we imagine it as 1, then the math becomes simple. The electric field strength, E, can have units of newtons per coulomb. It can also have, and we'll get to this later, volts per meter, but it's a good idea to know that from the outset. So 60 volts per meter is a measure of electric field strength, just as 60 newtons per coulomb. And 60 volts per meter is 60 newtons per coulomb. That's interesting. By substitution and expansion, we see that the separation between the mother charge and the point of interest affects the electric field in an inverse square relationship. And we can get that by saying, oh, I have an expression for the electric force. That would be, so it would be E is equal to, well, let's have a look. What was this? This was KE big Q, little q, over R squared times the unit vector. And we're going to divide that by little charge. Now, here all right, if you want, I'll do it like that way. I'll call that Q naught and Q naught, just to keep my math the same. Clearly, this naught is an optional symbol, but, you know, it's like sometimes they use it, sometimes they don't. Which gets me to E is equal to KE big Q over R squared times the unit vector pointing in the right direction. Notice, little charge is not included. You don't need the little charge to establish the electric field. The electric field is established by the big charge. So in a way it's trivial, and in a way it's really subtle. So it's one of those things where I remember thinking I'd got it, and then it bit me because I didn't have it. And then I thought I'd got it, and then it bit me. So it's worthwhile really spending a bit of time on this and trying to drive home the fact you do not need a second charge to have the electric field. You have the electric field caused by the first charge no matter what. And both charges have their own electric field, but we often talk about the field caused by the big charge affecting the little charge. We try not to have the field caused by the big charge and the field caused by the little charge affecting the little charge, because it gets complicated and it's redundant. So there's an awful lot of kind of like quite sophisticated choices been made when we analyze these problems that are not obvious until I mean, at first you don't even occur to you. You know, the possibility of both charges having an electric field doesn't seem obvious, and then when you get in a bit more depth of understanding, it occurs to you and you don't know what to do about it. In physics, it's like the first cut always seems straightforward, and then it gets complicated because you're thinking about it. And that's why studying the night before is disaster, because you just learned enough to be dangerous and you've not resolved any of it. And then you've got to spend some time to sort out the mess. So there we have it. I can turn around and say my electric field is equal to my force per unit charge, or I can turn around and say my electric field is all about the original charge. Two ways of writing down the same thing. Electric field and electric force. A large point charge Q establishes an electric field. Applying F of A on B would give me that. QA, QB over R squared times the unit vector. To the situation, so I shove in that, and then I say if I apply the E is equal to FE over Q naught, I get back to that. So I just derived that expression again. I don't know why I did this the second time, but I just derived that expression again. What is the magnitude of the electric field on a point that is 3 meters from a 6 coulomb point charge. So here's my 6 coulomb, call it positive. Here's my point, and that is 3 meters away. And I want to know my magnitude of my electric field. Let's visualize it. It's E, and it's going to point in that direction because it's going to be going away from a positive. With gravity, we always think about matter, so it's a boulder on a hillside. With electrostatics, we've got to think of the equivalent, and the equivalent of a boulder is a positive charge, not a negative charge. Negative charge is like a bubble, like a bubble underwater, you know. So think of positive charges like boulders. So, okay. Maybe I should. So my visualization is, that's electrically. This is the gravitational equivalent. I think of the positive charge as being like a volcano. And there's my point of interest. And which way would a boulder roll? It would roll down the hill. Well, that's the same direction that my electric field points. I want to find out the magnitude, so I can turn around and say E is equal to KE big Q over R squared, which equals KE, and big Q is going to be 6 over R squared is 3 squared, which is 2 over 3 KE newtons per coulomb. E is equal to 9.9 times that would be 6 times 10 to the 9 newtons per coulomb. Did I do that right? Good. Well, it's not bad. It looks so. No, I should have said it all on the tape. So what we just discussed was basically comparing and contrasting these equations and how it's so important to compare and contrast them. They're both inverse square relationships. The force depends upon both the charge, mother charge and the child charge, and the electric field only depends upon the mother charge. But they're both inverse square relationships. Let's do the next little bit, which is we basically imagine a whole bunch of charges. And again, we have this idea that the total electric field, and now we don't have a charge of interest, we have a point of interest. We have the sum of all the individual electric fields at that point of interest caused by these charges. Now there's an interesting point. I'm drawing these as long arrows and short arrows, but I'm only talking about the effect at that point there. So this is not a displacement, this is an electric field vector, which is quite subtle. But it's a way of visualizing. And I can sum all these guys up and I would get one overall vector, and I suspect it would be something like that if we added them together. It would be something like that. It would be pulled over more to one side than the other, etc. By the way, can you tell me, that electric field caused by that charge, is that a positive charge or a negative charge? Positive, because it's a repulsive field. It's a repulsive force which gives you a field going away. What about this guy, positive or negative? It's pulling towards it. So boulders rolling downhill. Oh, that's a negative. That's a negative. That's a negative. Okay, so visualize, visualize, visualize. And again, I'm going to just fly through this. Basically, it's the same problem we had before, but now it's talking about electric fields. So I have an electric field there, an electric field there, an electric field there. And in this case, it says the electric field at any point 2 meters away from an individual charge is 6. So that's 6 newtons per coulomb, 6 newtons per coulomb, and 6 newtons per coulomb. And that's 60 degrees, and that's 60 degrees. I kind of leave you to do the rest where you go. It's 6 plus 6 cosine 60 plus 6 cosine 60, and that equals 12 newtons per coulomb to the right. I mean, yeah, it's one of, they like to add that kind of thing. I don't like them so much. Let's generalize. And let's say that we have an electric field due to a continuous charge distribution. So we have a cloud of charge. And we take a little cube of it. And we say, I'm only going to think about that little cube of charge. And I got a point of interest. And I'm going to say, what is the influence of that little cube of charge on that point of interest? And it's my delta E, my little bit of electric field. And I have a million of these things, and I get a million of these arrows, and I vectorially add them up. And in fact, as engineers, that would be a good approach. It's called an iterative method, and you can divide a complicated but detailed cloud of charge into a whole bunch of little cubes of charge, and you run it through a computer program, and it adds all the vectors for you, and you get a decent answer at the end. We can quibble about detail, about a thing called bit noise and the like, but you get a decent answer. The more little cubes you get, the better the answer you get, etc. Physicists tend to say, oh, let's assume that everything's spherical, and so we can only do math on simple stuff. And we tend to, there's an old joke about a spherically symmetrical horse. You want to do work on a horse, but I'm a physicist, so all I can talk about is spherical things, so it's a spherically symmetrical horse. It's like it's nonsensical, but that's that's the approach we'd use. A good, powerful engineer can do both. You don't need a computer to do something with a high degree of symmetry. You use calculus, but you do know the MATLAB good enough that you can do something that's complicated. Physicists tend to do an awful lot of calculus and have one class using computer stuff. And that's too little to some extent. So I remember talking to my mentor. We all need mentors. And I didn't often have a mentor, but there's been like 3 times in my life when I've had a mentor. And the last one I'm still in touch with. And although I only worked for him for 2 years, in effect, we stayed in touch. And he's my go-to person for not just some technical things, but also for management things and philosophical things and the like. I remember him raising this issue with him, and he said, well, of course, the best engineers can do both. You need enough calculus that you can do the simple stuff with symmetry, and you need enough computer stuff that you can just jump on the computer and do it. But it's not an either-or, I do agree with that. So what we do is we divide a continuous charge distribution into small elements of charge delta Q. For each one, the equation is going to be our standard equation, which is E is equal to KE, my little bit of charge over R squared times the unit vector pointing in the right direction. So the total electric field is the sum of all these little bits. And if I take this to the limit, then I get my integral of all my little bits. It's the integral of dE, which is the integral of KE dQ over R squared. And there's one thing that, this is maybe showing my math ignorance, and it's like, why is it the little bit of Q rather than a little bit of R? And I think it's because you're dividing this up into smaller and smaller little squares, But there's 2 variables there. There's R's a variable and Q's a variable, and one of them you're making the little bit of, and the other one you're not. And it's because you're making it a little bit of a square, you have a little bit of Q.
What we're integrating with respect to?
Well, it looks like that. I'm respecting it with respect to Q, aren't I? Because that's what I'm going to end up doing. That's the point. I got to integrate. I got to get the thing in the terms of what I'm going to integrate with respect to. Consider a rod of uniform charge. So here's my rod of uniform charge. 9 coulombs. The rod lays on the x-axis. It extends from +3 to +7. So let's do that. +3 to +7. Use Coulomb's law to show that the electric field at point P, which is located at +1, is that number there. Okay. So I want my electric field. This is positive charge. Let's say positive charge. So let's say my electric field is pointing in that direction. I don't care because it's asking for a magnitude, but let's just imagine it like that. And I can say, well, my electric field is equal to let's just write down the base equation. KE Q over R squared. So that means that for a distributed charge, my E is equal to the integral of ke dq over r squared. And my dq, well, let's represent that. There's my dq. And my q total is equal to 9 coulombs. So let's do it. And we got a problem. Because this is saying integrate this with respect to q, and I don't know how to do that. So I need to change what my integration is with respect to. So I need to do I don't know how to integrate 1 over r squared with respect to dq. I need to convert that from a dq to a dr. So I'll come back and I'll do a bit of physics, and this is the physics bit. I say, well, there's my dq, and I'm going to call this dr, or I can call it dx, I don't care which. Let's call it r. So this is going to be dr. My dr is my little bit of width. So I say, from a physics point of view, my little bit of charge is going to equal to my little bit of width times the charge per unit width times, let's write that in words, my little charge is equal to little width times the charge per unit width. So if it's a wider little width, it's going to get more charge. If it's a smaller little width, it'll have less charge. And this would be, if you like, the linear charge density. So this is going to be dr times the linear, let's put this down a bit, dq is equal to dr times the linear charge density. So dq is equal to my linear charge density, dr, times my linear charge density. My linear charge density is the total amount of charge, which is q, over my total amount of width, which is L. Let's call it L. Okay? Now, I can shove numbers in now, or I can hold off shoving numbers in. And when I was starting, I'd shove numbers in early, but as I've got older, I hold off on shoving numbers in because sometimes letters cancel. And you can see what happened, and you can check your work easier. So let's just hold off for a minute or two. I might put numbers in soon. So that's a little thought to itself. That should be, I'm sorry, DQ. I'm mixing my symbols here. So E is equal to the integral of KE over R squared dr times Q over L. Let's take out the constants. E is equal to, well, Q's a constant because it's 9 coulombs, and L's a constant because that 3's not going anywhere and that 7's not going anywhere. Integral 1 over R squared dr, which equals Q over L, integral of R to the minus 2 dr.
Did you mean to pull out your KE?
KE, I completely left it behind, didn't I? KE. Thank you. So E is equal to KEQ over L. And this is going to be, so what does that become? It becomes my 1 over, reduce the power by 1 and put it in the denominator. 1 over R. And now I really need to put my limits in. And this is what catches people. What does R represent? It's the radius of the cylinder, the sphere, which is really your separation between your point of interest and your little bit of charge. And the smallest radius is that. which is 3 minus 1, which is 2. And your biggest radius, because that little bit of charge can be all the way over there, is that, which is 6. And so many people want to put down 7 and 3 because they're the only two numbers they're given. You know, it's like, I got to use the limit. Oh, it must be the 7, must be the 3, because they were the only two lengths I was given. And this is again why good math on a bad diagram gets you nowhere. So I'm deliberately not putting P at one end of my piece of charge. I know what I'm doing. I'm trying to see, do you know how to work out your limit on this? Can you visualize? It's all about visualization. So E is equal to KE Q over L, and this is going to be, what's that going to be? Well, let's put some, well, I didn't put numbers in, but let's do it now. So minus 1 over 6 minus 1 over 2. So let's put some numbers in. KE. What is Q? Q is 9. And L is 4. And then minus and minus make plus, so that would be 3 over 6 minus 1 over 6. So E is equal to KE 9 over 4, and that would be 2 over 6. So that would be 2 9s are 18 over 24 KE, which equals 0.75. Is that right? KE newtons per coulomb. That's a really good test question. Something like that.
Is it negative? Oh,
It's asking for magnitude, yeah. If I asked for the vector, it would be a negative, yeah. That kind of thing may well be on the test. It's a good test question. And why? Because we're going to do this process of recognizing I can't do that integration. Let's change what I'm integrating with respect to. Comes up time and time again. I will not move this point of interest off the axis. I'm going to keep it simple to begin with, and later on we'll do more complicated things, you know, but for this question, it could be to the right of it, could be to the left of it, could be in negative land, could be in positive land. I can mess with where it is. You've got to look at this diagram and turn around and say, oh, that distance is 2 meters, that distance is 6 meters, and be able to figure it from there. Yeah.
So E always going to be negative?
Is E always going to be negative? No. I mean, it's not negative here, in fact. If I'm talking, what do you mean by E, I guess is?
The vector.
Oh, vector E. Vector E is going to be an IJK, and maybe it's got positives in and maybe it's got negatives in. On a single line, if it was only in X, E could just as easily be positive X value as a positive, could be positive 1X, the direction could be negative 1X. It depends. If I'd have put my, in this case it's a negative, if I'd have put my point of interest over here, it would have been in the opposite direction.
Okay.
Yeah, so.
But let's say if it's on A, let's say that it's on A.
I'm sorry?
Let's say that the electric field is going to be positive 1 if it's on positive.
No, it's position, yeah, the point of interest, yeah. You're moving the point of interest. So where you want to move it to?
To positive 8.
So positive 8, yeah. So it'd be like here, yeah. Then it would be in that direction, be a positive vector in X.
Which one would be the limit of integration?
It's going to be that distance
to 5?
and that distance. So if it was 8, that would be 1, and that would be 3 from 8 gives 5. Yeah.
Why would it be -1 and -5?
That's where I'm coming from. Because it's gonna be positive if it's gonna
Whoa!
be
What negative 1 and negative 5? I've not said a negative 1 and negative 5.
So why wouldn't it?
Oh, because it's a separation.
But if you do that integration, the vector will be negative 2, right?
No, it's still going to be a positive value. The integration is going to be positive because I'm putting positive limits in.
Okay.
But now if you want the vector, you got to look at the diagram and say, I need a unit vector to point in the right direction. That's where you get the sign positive or negative from. But I'm asking you for the
But the
magnitude.
integration always gonna come out positive.
Integrations come out positive unless it goes, unless you go on the opposite side of some line. But these integrations
Okay.
would be positive because the limits are going to be positive numbers. Yeah, cool. Yeah. So good test question. This last one, frankly, let me tell you about it. So basically what we have is we have two metal plates, one's positive, one's negative. I'm making the top plate negatively charged and the bottom plate positively charged. And so a electron coming in would be repelled by the negative and it would want to go in that direction, but because of the repulsive force it would go like that. Just like throwing an object across a room. And so we can actually simulate gravity. We can say, well, for the electron, the force is equal to the charge of the electron times the electric field. And of course, F still equals ma, so we put these two guys equal to each other and I get E is equal to ma, so I can work out that A is equal to E times, little e times the electric field over m. So then I say, oh, that's a real acceleration, and I know where there's a constant acceleration, I can use my equations of motion. And so I say Vf equals Vi plus A times delta T, and I can do some problems on it. I'm not so interested in that. So I never get time to go through it, so just know it's there. You know, I got bigger fish to fry. Don't pack up yet, I've got 5 minutes. Hold on.